Today we are going to start our conversation about area under the curve. Okay, so today we are going to work on drawing rectangles under our curve and adding up all of the rectangles to approximate the area under a curve. Can you find the area of a rectangle? Then you can do today's lesson. Okay. So we will have to teach Aaron how to find the area of rectangles. Fair enough. Okay. So what we're going to work on today is we're going to take the right side of the rectangle, the left side of the rectangle, or the midpoint of the rectangle, and place it on our curve and add them together. What the heck am I talking about? Let me show you. Okay, so here I have a curve, and here I have rectangles. Do you notice how the left corner of our rectangle is on the curve? Okay, now these green rectangles, these are right end, so the right corner is on the curve. Or here, the midpoint of our rectangle is on the curve. Do you see that? Okay, so I'm going to go back to our red ones. What is true about the area of these rectangles versus the area of these rectangles? Which is going to more accurately approximate our area? Okay, so the more rectangles, the more accurate our area, correct? Okay. Also, the more rectangles, the more annoying it is to calculate. So we kind of have to find like a little bit of middle ground, okay? But our goal today is to use these rectangles to find the area. Now, what else do you notice about all of these rectangles? Are they, obviously they're all different heights. Are they different widths? They're all the same width, okay? And if they all have the same width, that's going to make your calculation a little bit easier. And their heights come from coordinates on our function. That's pretty nice too, okay? Okay, so this is what we're going to do. We are going to have to decide how many subdivisions to use. And typically, you are just going to be given that number, and we're going to call that number n. Okay, so when you see n in any of these calculations, we're talking about the number of rectangles we're going to use. I will tell you whether we're going to use left, right, or middle approximations, or they might say, find the over approximation, find the under approximation. Okay, and we'll talk about how we know which is which. Okay, the widths of our rectangles are going to be, we're going to call delta x. So the change in x is going to be how wide all of our rectangles are. And we're going to calculate that by taking the range of our x values. B minus a is where do we stop minus where do we start, all over the number of rectangles. And the heights of our rectangles are going to come from the function itself, okay? Since we're placing these rectangles so that a corner or a midpoint is on the function, then the function is going to help us figure out what the heights are. Sometimes we miss our middle school / freshman year days. So I'm handing out something we're going to use to take notes on for both today and tomorrow. Okay? So this is what I want you to do. Do you see this line in the middle? It's not quite in the middle. You're going to fold on that line so that area approximations are still there. So you can maybe, if you need to fold it backwards first and then fold it forward. Okay. We did one of these last year in pre-calc, I think. Okay. Look at me up here. Once you have it folded, you are then going to cut on the horizontal lines to the fold so that you have 4 book flaps. See this? Ready? Okay, now do the cut. So we are going to fill out the first 3 of those book flaps today. And tomorrow we're going to talk about the 4th one, the trapezoidal approximation. What are you calling stupid? What did Isaac say? Oh, I thought you said. Okay, when you're done cutting, put the scissors back in the caddy and just be patient while we wait for the slow pokes. Like Austin right now. Sorry. Bacon bread. All right. Thank you. So here we go. We're going to talk about the left-hand sum first. So I want you to take the very first flap and open it up. Okay, and let's talk about, we want to go, well, I'm saying the area of f of x squared over 0 to 2. So 0 is our A and 2 is our B, okay? And we're gonna go ahead and I'm going to tell you that let's do 4 rectangles, okay? So if n is 4, okay, then we're gonna find delta x by taking b minus a over n. So what is our delta x? 1/2. So now I want you to close the flap and we are going to draw our 4 rectangles so we at least know what the heck we're doing. Okay. So from 0 to 4, we're going to have rectangles of width 1/2 or the left corner touches the curve. Okay. Just making sure we got things written down that we need. Tiernan, you got what you need? Cool. So let's come up here. So if I go from 0 to 1/2, the height of our rectangle would actually be 0 because that's where the left corner is. That's boring. Let's go from 0, or excuse me, 1/2 to 1. I'm going to draw so that the left corner reaches. Then from 1 to 1.5, then the left corner would touch here. And then from 1.5 to 2, our left corner would touch here. Just from looking at this picture, is this area going to be an over approximation or an under approximation to the actual area under the curve from 0 to 2? Under, because we see white space under our curve, right? Or in your case, pink space. Yeah. So now let's open the flap. Okay. This is what we're going to do. Our area. Okay. How do you find the area of a rectangle? Length times width. What is the width of every single rectangle? 1/2. So that's nice. Okay. Here, from 0 to 1/2, 0 is on the left side. So I'm going to take 1/2 times the function value at 0. Plus, from 1/2 to 1, the left side is 1/2. So our width times our function height. Plus the width times our function height. Plus the width times our function height. Okay. So on the left side of the rectangle, I'm plugging that x value into our function to get how tall the rectangle is. Now, do you find it annoying that you wrote 1/2 4 different times? So if my width is the same for all of my rectangles, could I just factor it out and write it one time? The answer is yes. Now, the y values are actually giving us the height of those rectangles. So whatever your equation is, you need to plug in these function values into these x values into the function. So we have 0 squared plus 1/2 squared plus 1 squared plus 3/2 squared. Okay, I'm getting these 4 numbers because I'm evaluating our function heights. Cool. What's our area? It is 7/4. Okay, so are we really gonna think about like 0 to 1/2, 1/2 to 1, 1 to 1 and a half? Okay. What do you notice about 0 to 1 and a half, 1 and a half to 1, 1 to 3 and a half? How far apart are those? How far apart of our rectangle? How far apart are our rectangles? Oh, they're 1/2. Okay. So if we are doing a left approximation, we are going to start with the left side of our interval, and we are going to increase our x's by delta x until we get our n rectangles. See what I'm saying there? So if n was 5, I would keep adding 1/2 until I have 5 rectangles. Okay. All right, let's skip down to our right-hand sum. And what I want you to do is open the flap for our right-hand sum. And I just want you to remember that our delta x is always going to be the same. So if n is 4, then delta x, b minus a over n, is going to be 1/2. I'm going to have you go to the graph on the front, and we're going to draw rectangles so that the right side meets up with the curve. Okay, in this particular picture, what's going to be true about our area approximation? It's an over approximation. Yes.
Is it over by the same amount or
No. Did you guys hear me when I said gotta skip to the right hand one, which is the third flap? Whoops. I said skip one. Emma did. Okay, so if we're gonna find the area under this curve, can we all agree that since our function or our rectangle widths are the same, we just keep it factored out? Okay. And this is what I'm gonna do. Since we have a right endpoint approximation, I'm gonna start on the right side of my interval. So this rectangle right here has height of f of 2. And then the next one over is 1/2 later, because that's delta x. And the next one is delta x over, and the next one is delta x over. And I'm gonna stop because now I have my 4 rectangles. Now, the good news is you are not going to have to draw these pictures every single time, okay? I'm trying to get to the visualization of what the heck we're doing. Okay. So here we go. We have 1/2 times. Now I'm going to plug in these to our function. What do we get this time? Times 1/2. So 15/4. Would you agree with that? Okay. Makes sense that this one is more. Okay. After a while, I'll tell you what the real area is. Okay. Okay, so 15/4 is too much. 7/4 is too small. Let's go ahead and talk about our midpoint approximation. So the midpoint approximation, we are going to get the height of the rectangle by the middle of the interval, okay, of each of our little subintervals. So remember, delta x is b minus a over n. And in this case, if n is 4, then our delta x is 1/2. Okay, boring. This is the third time we've done that. Okay, when you've gotten this written down on the inside of your flap, let's go ahead and draw our pictures. Okay, now the height of our rectangle is going to be determined by the middle of the rectangle. So from 0 to 1/2, the height is happening at f of 1/4. So what's happening with these rectangles? There's like a little bit over and a little bit under the curve. Would you agree? Okay. Now, the midpoint, kind of annoying. There's a little bit more thinking involved because we have to get that first midpoint. But same as all of the other examples we've done, our rectangles are delta x in width. So our midpoints are going to be delta x apart. So our area Length times width plus length times width plus length times width plus length times width. These all have the same width, so I'm gonna keep that factored out. Now, we have to think about where our first midpoint is. So if our first rectangle is stretching from 0 to 1/2, what is its midpoint? 1/4. So f of 1/4 is our first midpoint. Now, delta x is how far apart these rectangles are, which is how far apart our midpoints are. So we're just gonna keep adding delta x to this 1/4. So if we add 1/2, we get 3/4. If we add 1/2, we get 5/4. If we add 1/2, we get 7/4. And that's my last midpoint because we have 4 rectangles. Also, not as much fun to calculate. We have some crazier fractions. That's fine. What do we got? 84 over 32. Okay. Hey, if you leave it like that, I'm not gonna be upset. But if it bothers you and you want to reduce it, you are more than welcome to. The real area under this curve from 0 to 2 is 8/3. Which one is closest? You're assuming midpoint. Okay. Depending on the curve, it's going to depend which one's going to be closest. But midpoint having a little bit over, a little bit under kind of evens it out a little bit, but it's still not going to be perfect. Okay. Let's transition back to your like normal notes. Okay, I want you to understand the difference between when we have rectangles under our curve versus hanging outside of our curve, and what that's going to mean for our approximation. Okay, so we can have inscribed versus circumscribed. Okay, triangles fitting, not triangles, these are definitely rectangles. I know my geometry, don't worry. Rectangles fitting under the curve versus rectangles hanging outside of the curve. So in these pictures, I have a decreasing curve, and what kind of rectangles are fitting underneath? The right hand, okay? Now, if I had an increasing curve, what kind of rectangles would be inscribed? Okay. Okay. So if I ask you to find the under approximation of the area, it will be important to note if our function is increasing or decreasing on that interval. for you to be able to choose whether to do right or left. Okay. For these circumscribed rectangles, this curve is decreasing and we have left hand rectangles. If we were to have an increasing curve, our right hand, that's terrible, rectangles would be circumscribed. What, Trini? We've been a lot less negative today. Thanks, guys. Because Matt has kept his mouth shut.
It's like you're
Heroes Day and what? Okay. Okay, we're going to find the upper and lower sums when n equals 5 from 1 to 2 of y equals 6 minus x squared. If we have time, of course. I want you to visualize 6 minus x squared. It's not working for you? Visualize 6 minus x squared. Dylan, what does it look like? Okay, it's an upside down parabola, up 6. So on the interval 1 to 2, what is true about our function? Is it increasing or decreasing? All right, it is decreasing. Okay. So if we want our over approximation, we're going to find our upper sum first. If we want our over approximation, our curve is decreasing. Are we going to find the right or the left endpoints? So what we're going to do, we first need delta x. And delta x is b minus a over n. Ew. 1/5. Cool. I'm going to teach you something really cool on your calculator to help you out. So please do not work ahead of me. Okay. All right. So we are finding our left-hand sum. So we have 1/5 is the width of our rectangles times. We have 5 rectangle heights that we need. We are going to begin on the left of our interval since we're doing a left approximation. So f of 1 plus delta x later, f of 5/4 plus delta x later, 6/4 fifths. Oh my goodness, Miss Holman. JK, 6/5, 7/5, 8/5, 9/5. I'm going to stop because I have 5 rectangles. I was in the mode of fourth. So sorry. So sorry. All right, you ready? Ready to shortcuts with our calculator? Okay, so in your calculator, here. For your calculator? I have a charging station up there. You could. Batteries. Okay, Kylie, you let me know when you're ready. Please go to y equals and type in 6 minus x squared. So this is what we're gonna do. I'm gonna type in 1/5 times the quantity. I'm gonna call up our function value at 1. So do you see the trace button and there's this F4? Hit alpha, F4. And y1 of 1 plus y1 of 6/5 plus y1 of 7/5. I'm hearing what? You do have to open the parentheses and close it. But it's easier than putting parentheses, 6/5 parentheses squared minus 6 plus parentheses 7/5 parentheses squared minus 6 plus. And especially if you have some crazy thing like x cubed minus 5x squared plus 3x plus 2. You don't want to type that in every time. That saves you some cramping, some time, efficiency, whatever. You're gonna have your calculator, you might as well use it. You didn't get the same answer as me?
I just got the one, that's why.
You got the same answer as me? Okay.
I forgot to put the Y one.
Okay. So we get 3.96, or if you want to write 99/25, you do you, okay? And then to find the lower sum, we would do the right endpoint approximation, okay? And what's nice about this is if we were to do it, we already have f of x in our calculator. And I'm not going to type it all in the calculator, but what I want you to remember is that when we are setting up a right-hand sum, please start on the right hand of your interval. So our right hand of our interval would be 2. So f of 2, and then we're going to go down by delta x. Oh, yeah, sure. I'm just very OCD about things being in order from left to right. Okay. But now I have 1, 2, 3, 4, 5 f of x's, so I know that I have my 5 rectangles. Okay. Tomorrow we're gonna do the same thing, but with trapezoid. We'll get there. We'll get there. Okay. So you need to do your homework tonight, and please pay attention to the gold sheet when it asks you to do midpoint as well. I think I like add something in there with like, hey, also do midpoint here. Also, please keep in mind that we're off on our gold sheet. So whatever lesson we do in class, your homework should match that, okay? So maybe it would be helpful for you to like cross off the days as we go through them on your gold sheet so that you know what we've done and what we're gonna do next, okay?